transistors, which act like electronic switches. In the normally off N-channel transistor, the ends of the switch, known as the source and drain, are electron-rich N-type regions. A small positive voltage applied to the gate repels the positive charges in the P-type substrate beneath the gate, but attracts electrons from the source and drain. This electron channel allows current to flow through, turning the transistor on. When the gate voltage returns to zero, the transistor is again off. In the normally off P-channel transistor, a small negative voltage to the gate repels electrons in the N-type region and attracts positive carriers from the P-type source and drain. These positive carriers beneath the gate conduct current. This on and off creates the ones and zeros of the electronic language. In the fabrication of these electronic switches, ion implantation is used to control the position and number of dopants. To see how this works, let's explore the early fabrication stages of our simplified CMOS transistor. Wafers are cleaned before and after every major step. In a furnace, pure oxygen reacts with the surface silicon. The result is a thin, glass-like insulator known as silicon dioxide. A photographic process is then used to pattern the silicon dioxide layer. Photoresist, a light-sensitive material, is evenly spread across the wafer. Inside an exposure system, ultraviolet light exposes a reduced mask pattern on the surface of the wafer. When developed, the exposed resist is removed. The exposed silicon dioxide, where the N-wells will be created, is then etched. After the hardened resist is etched away, the wafer is ready for ion implantation. Ion implanters are complex systems, which are classified according to either their energy level or current range. The higher the energy, the deeper the ions penetrate the silicon substrate. To create the deep N-well of our CMOS transistor, a high-energy implanter is used. All ion implanters have basic subsystems in their beamline. Positive ions will move through these systems in response to internally applied electric and magnetic fields. Magnitude and polarity of these fields will determine the speed and direction of the ions as they move towards the process chamber. In the end station, wafers are loaded, placed in the path of the ion beam, and unloaded. It is here, in the load lock, that the wafers are first introduced to vacuum. Vacuum is crucial to ion implantation because it removes most of the densely packed molecules found at atmospheric pressure. This vacuum allows the ion beam to move freely through the implanter without colliding with unwanted atoms and losing momentum. A variety of roughing and cryopumps create a baseline vacuum which will remain throughout the process. Behind the wafer loading area, we see the back of the process chamber where implantation occurs. Inside, we find the large disc with 13 pads. During implantation, it will spin at over 800 revolutions per minute. The wafers, coming from the load lock, are edge clamped to the pads to hold them in place when the disc spins at full speed. The beveled edges of the disc's design eliminate sharp corners that might trap unwanted particles. Encased channels use water to keep the wafers cool. A slot on the disc allows a sampling of the beam to come through so its current can be measured for uniformity. The angle of the implant is very important. The disc chamber can tilt in the alpha direction or in the beta direction. This tilt of the wafer prevents channeling where ions enter the crystal lattice along channels of major axes and planes and travel to unpredictable depths. As the disk spins, it moves from left to right. This provides the horizontal and vertical scanning motion needed to uniformly implant the entire wafer. Beyond the process chamber are the main power, gas cabinets, and the ion source assembly. Dopant ions come from gases that contain the desired atoms. This ion implanter uses boron trifluoride as the source for the boron p-type implants, and phosphine and arsine gases for phosphorus and arsenic ions used in the n-type implants. Most of these gases are highly toxic and must be stored in a well-ventilated, safe delivery system gas cabinet.